Paderborn University in Germany. I will talk about correct optical and universal noise figures. How do you determine the noise and gain properties of an amplifier? You have a signal source, a bandpass filter, and a power meter. You measure the noise of the signal source alone and then with amplifier. That's the standard electrical measurement. Now assume that you are inserting a power meter here. The power meter, like this one, consists of a square and a low-pass filter. But this low-pass filter has a wider bandwidth than this, and it has a smaller bandwidth than this bandpass filter. Is this extra power meter helpful? Of course not. But now we are in the optical domain, and this is a photodiode. But this leads to problems, as we will see. Here is the definition of the gain of an optical amplifier with simulated emission and absorption. This rises exponentially versus the time which this needs during propagation. There is the spontaneous emission factor. Here is a mean number of detectable output noise photons per mode. And the mean output noise power is related to that. You just take this number, multiply it by HF, then you have an energy. My tilde is, in my case, my divided by gain. If you take this energy and you divide it by the observation time, or if you multiply it by the bandwidth, then you have the power spectral density. So this times the optical bandwidth is the output noise power of an optical amplifier. The standard definition of noise figure is signal to noise ratio at the input divided by signal to noise ratio at the output. The standard definition of optical noise figure by de Surveer, I call it here F of photon number fluctuations. This says that the powers here are those which you measure as electrical powers behind a photodiode. So here is the optical amplifier, bandpass filter, photodiode, and then you take the square of the photocurrent to have the this power at the output, and without the amplifier you measure a smaller power at the input. This gives you immediately the quotient of these two terms must be the gain. But when to measure the power, you take the square of the photocurrent, and the photocurrent is itself proportional to optical power, then the power which you measure here is proportional to the square of the optical power. So the power gain you have here is the gain is the square of the true gain. This means no more optical dB are allowed. We need so-called electrical dB. The fiber loss is at 50 nanometer, 0.4 dB, not 0.2 dB per kilometer. Now I replace my my photodiode by a thermal power meter, because this must be allowed. I still can measure, for instance, the signal gain, which is G squared. When I have the thermal power meter, I can decrease the frequency until I'm in the electrical domain. Then I find that any electrical amplifier with 20 dB gain has 40 dB gain. All powers must be proportional to squared powers, also mechanical powers. Work is time times square root of the so-called power. So this either physics is correct or this is an optical noise figure. I think physics is correct. And the problem is that the square of the field, the photocurrent is proportional to the square of the field amplitude, but the SNR power is proportional to the square of the optical power. So there's a conflict with 150 years of science. There are more problems. an ideal optical amplifier has a noise figure of 2, whereas for an ideal electrical amplifier, the noise figure equals 1. Noise happens on the field basis. Looking at the power is insufficient. An ideal direct detection receiver for intensity modulation without optical amplifier needs, ideally it needs 10 photons or photoelectrons per bit for a bit ratio of 10 to the power minus 9. With ideal optical amplifier, it needs 38, but the quotient of this is not 2, which the noise figure claims. For a differential phase shift keying, with or without amplifier, the ideal receiver sensitivity is 20 photoelectrons per bit. This quotient is also not equal to 2. The direct detection receiver is nonlinear in the sense that the photocurrent is proportional to the square of the optical field. Therefore, we get non-Gaussian noise. The amplifier noise figure depends on power and bandwidth. But in the electrical domain, we have a linear receiver, Gaussian noise, and constant noise figure. Unifications of all prior optical noise figures with electrical noise figure is inconsistent. What can we do? Well, we need a linear receiver and linear optical receiver, and that is a coherent receiver. It also must have 2 available quadratures. For example, after an electrical after an electrical amplifier, I can down convert the in-phase portion and the quadrature portion of a carrier independently with mixers. And that is also possible in phase and quadrature optical receivers. They have an optical 90-degree hybrid at the input. We superimpose the optical signal with an unmodulated local oscillator signal, and in this photodiode we get this field minus J times this field, and here we get this field minus J times this field. I can slightly reformulate this, and I can calculate the photocurrent here, and also here. Here is an extra 90-degree phase shift or path length difference. So here you have the down conversion of the optical field in phase and here in quadrature. 2 available quadratures. I can calculate the photocurrents. The electrical received field contains the amplified signal power and in phase and quadrature noise caused by the amplifier with the noise power which we found previously. The photocurrent is responsivity times power, and the photocurrent also gives us shot noise. When we take the difference of these 2 photocurrents, we get a difference photocurrent, same here. And then we can neglect terms because the local oscillator power, this unmodulated laser, is very strong. And in subtraction, the DC term cancels, and we get this interference term here and there. This is not interesting. We look only at the in-phase part. We take the difference with plus and minus signs, so the interference term adds. And this is my difference current with the in-phase noise of the optical amplifier. In the second difference term, we have the quadrature noise of the optical amplifier, but that's not interesting here. The photocurrents cause shot noise. The shot noise is proportional to the photocurrent, and in total we get this signal to noise ratio at the output. Here we have the received the signal power, which is amplified, and this term is due to the coherent optical reception. Here we have shot noise, and here we have optical amplifier noise, which is amplified. We can cancel a few terms and get this expression. Here's the input referred number of detectable noise photons per mode. This is 1 over G. This is half the photon energy. Here's the signal energy in the observation time. When I remove the amplifier, this is 0 and the gain becomes 1. So I get this signal to noise ratio at the input. The quotient of the two gives this optical noise figure for in-phase and quadrature signals. It obeys the usual electrical noise figure definition. It is the SNR degradation factor in a receiver with 2 available quadratures, in an ideal receiver with 2 available quadratures. The power is proportional to the square of the amplitude, not taken to the power 4. The thing is linear. The ideal noise figure equals 1, and we have purely Gaussian noises. We can convert this true noise figure into the previously defined noise figure and vice versa. For large gain, we simply have 3 dB less for the noise figure, or half of it when we consider noise factors. So this needs to be corrected in 10,000 heads who have learned this noise figure. We can measure the optical noise figure easily. We measure the signal power alone. We measure the amplified, the noise power behind an amplifier. Here we get a factor of 2 usually because there are 2 amplified polarizations. And we measure the power with signal and noise. And from that, we can calculate, from these 3 measurements, we can calculate the gain, and we can calculate the input referred number of noise photons per mode. In optical detection, there's a specialty, homodyne detection, which has 3 dB more receiver sensitivity. Things simplify here. A few equations are multiplied by 2, and finally we get this a very similar noise figure as here, but this term now gets multiplied by 2. Here the noise figure of an optical amplifier is at least equal to 2, because yeah, when you have a homodyne receiver. But the homodyne receiver is a special case. You don't have this usually in the electrical domain. Generally, we can have source noise, we can have added amplifier noise, and we can have detection noise. When we calculate the noise figure from all that, we find that the noise figure gets a form constant, where this is the source noise fraction. Source noise divided by source noise plus detection noise. And 1 minus A is the detection noise fraction. This is divided by G, by the gain of the amplifier, because if we have much gain here, the detection noise here plays a smaller role. So we have a 1 over G here. And this is added noise by the amplifier. If the noise figure has this form, we find that Free's formula is fulfilled. So any noise figure which has this form fulfills Free's equation. And this is the case for all previously defined and also for my noise figures. They've all fulfilled Free's equation. Let us compare this is my tilde at the input. The input referred number of noise photons per mode is spontaneous emission factor times 1 minus 1 divided by G. FPNF has only 1 available quadrature. Also, it is nonlinear, but noise figure pioneer House has defined a similar noise figure. It didn't tell that it is for homodyne, but it is obviously for homodyne. So it is equal to that and to my homodyne noise figure. But he has a different form for all frequencies. So it is identical. These two are identical only in the optical domain. And Hermann Haus has also defined another noise figure. This assumes source noise, as you can see here. Detection noise means 1 over G. and this means source noise. But in the optical domain, there is no source noise. And also, this noise figure is not the SNR degradation factor in any known optical receiver. So it is not a noise figure. When comparing the different noise figures, we find agreement between the electrical noise figure and one of the optical noise figures only for the optical in phase and quadrature noise figure. Two available quadratures, ideal, it is linear, it is the SNR degradation factor. This is fulfilled. So we can combine the two to a combined optical noise figure for all frequencies. In earlier times, people said the minimum noise figure of an optical amplifier is 2. Well, according to the foregoing and excluding this one because it is not the SNR degradation factor in any optical receiver, but taking all other optical noise figures, we find that the ideal optical noise figure turns out to be equal to the number of available quadratures in the amplifier divided by the number of available quadratures in the receiver. And when FP and F was defined, they said we have a phase insensitive receiver, direct detection, it works in terms of noise, it works like homodyne. Well, there are a lot of differences, but you get the same noise figure. And here the ideal noise figure of 2 was defined or was found. But with the same right, I could say, wait, the normal case is that I have 2 available quadratures in the receiver and I have a phase sensitive amplifier. In that case, my ideal optical noise figure equals 1/2. Of course, this is rubbish and this is rubbish. What count, or I shouldn't say rubbish, but it does not make sense. What makes sense is to have the same number of available quadratures for the amplifier and for the receiver. The most common case is 2 available quadratures in the amplifier and in the receiver. At least that's how it is in the electrical domain, and we have kept the same for the optical domain. Homodyne is a special case. A phase-sensitive optical amplifier will have a noise figure of 1 if put in front of a direct detection homodyne receiver. Of course, you cannot say we have the electrical noise figure and you have this optical noise figure and they are never joined, because in the low terahertz region, you would find unequal noise figures for the same usage of the same amplifier at the same frequency. Also, the noise figure must be detector independent. So we must, therefore, the optical noise figure works only, it works only for this noise figure in the optical INQ noise figure. To avoid misinterpretation, the earlier noise figure could be called a high power optical chi-squared noise estimator or similar, or photon number fluctuation indicator or similar. It shouldn't be called a noise figure, because if it is a noise figure, then by definition, any amplifier with 20 dB gain has 40 dB gain and other nonsense. Because how the noise figure is calculated, this has been defined by Hermann Haus. Okay, I would not call this a noise figure. You should call it differently. My 1 quadrature noise figure is similar to this. I have shown to you that all prior optical and unified noise figures are in conflict with the electrical noise figure. A noise figure without special name is expected to be the SNR degradation factor in a linear system with 2 available quadratures, and probably Gaussian noise, like the electrical noise figure. The only optical noise figure which fulfills this is the optical in phase and quadrature noise figure FO. It is larger or equal to 1, like the electrical noise figure. The a useful receiver here is a coherent optical INQ receiver, because that's a linear field sensor. The linearize the quadratic field behavior of photodiode. At high gain, this noise factor is half of the traditional noise factor, or the noise figure when expressed in decibel is 3 dB less if gain approaches infinity. The electrical and optical noise figures are limit cases of one optical in phase and quadrature of one unified noise figure for all frequencies. Today, this, instead of the electrical noise figure, plays a role at today's low temperature electronics at 4 Kelvin. That's all I have to say. Optical amplifier adds Gaussian in phase and quadrature field noise, that's the wave aspect, and the photo detection adds shot noise, which is the particle aspect. Thank you for your attention.